Chapter 2, Information Measures. In this chapter, we are going to learn some basic tools in information theory. First, we will talk about some basic concepts in probability. We will then introduce Shannon's information measures and prove some of their properties. Then we'll talk about some other useful information measures. And then we'll talk about some useful identities and inequalities in information theory. Section 2.1 is about independence and Markov chain. Here are some notations that will be used throughout this course. Capital letter X denotes a discrete random variable taking values in a set script X, called the alphabet of the random variable X. P of X is the probability distribution for random variable X. Support of X is denoted by S of X, and this is a set of all outcomes X such that the probability is non-zero. If the support of X is equal to the alphabet of X, that is, all the probability masses are positive, then we say that P is strictly positive. Non-strictly positive distributions are dangerous in the sense that we need to handle them with great care, and we are going to look at an example in proposition 2.12 to illustrate this point. Definition 2.1 is about independence of two random variables. Two random variables x and y are independent, denoted by x perp y, if pxy is equal to px times py for all x and y. Definition 2.2 is about mutual independence. For n greater than or equal to 3, random variables x1, x2 up to xn are mutually independent if px1, x2 up to xn is equal to px1 times px2 all the way to pxn for all x1, x2 up to xn. Definition 2.3 is about pairwise independence. For n greater than or equal to 3, random variables x1, x2 up to xn are pairwise independent if xi and xj are independent for all ij between 1 and n. That is, any two of these random variables are independent. It can be shown that pairwise independence is implied by mutual independence, but not vice versa. Definition 2.4 is about conditional independence. For random variables x, y, and z, x is independent of z conditioning on y, denoted by x perp z given y, if pxyz is equal to pxy times pyz divided by py, if py is bigger than 0, and pxyz is equal to 0 if py is equal to 0. Here are some remarks. First, if py is bigger than 0, then pxyz is equal to pxy times pyz divided by py. Here pyz divided by py is equal to pz given y, and therefore we have pxyz equals pxy times pz given y. So we can as well use this in the definition for conditional independence. Conceptually, when x is independent of z given y, x, y, z are related as shown in the following diagram. We start with a random variable x, and then we pass it through a channel py given x to obtain the random variable y, and then we pass y through another channel pz given y to obtain random variable z. So the joint distribution of x, y, and z is given by pxyz equals px times py given z times pz given y, where px times py given x can be written as pxy, and so we have pxyz equals pxy times pz given y as we have seen before.